Page 3, still doing some density stuff. This one says if you made some cubes, let's just make one cube. One cube, and it says 3.5 centimeters by 3.5 centimeters by 3.5. What's the volume in cubic centimeters? 3.5 times 3.5 times 3.5, 42.9. So then what's the volume in milliliters? This is going on to that assumption that we remember that the milliliter and a cubic centimeter are exactly the same size. They designed the metric system that way based on common things. So it is also 42.9 milliliters. If you had a cube from part A, I have to go back to page 3, made of lead, what would its mass be? Well, if I have a 42.9 centimeters cubed, or milliliters, it doesn't matter. Before I even go get a number, I'm going to let the units lead. The numbers will follow. I need cubic centimeters on the top. What I really need to know is its mass. Mass is in grams. So let me go back to page 3. Let me find lead. Lead is 11.35 grams per milliliter. What does that mean? 11.35 grams. That means I put the 11.35 here next to grams, and 1 milliliter or cubic centimeter is on the bottom. 42.9, I already have it there, times 11.35, 486.6 grams. Okay, gas relationships. I had to pull up some notes, and you'd be able to use these notes about relationships, about proportionality, about relationships between the pressure and the temperature and the volume and the number of moles of gas. We had lots of notes that looked like this. When it first comes time, we just have to start reading and filling in this little chart. One thing to remember, though, is anytime we see a Celsius, we can't use Celsius. We have to change it into degrees Kelvin. So a gas initially at 981, that's a pressure. And 35, I have to turn that into Kelvin. 273 plus 35 is 308. I have those notes written right here. On Kelvin, add 273. Occupies a container with an initial volume of 5 liters. By changing the volume, so I must be getting a new volume, the pressure of the gas decreases to 54. As the temperature is raised to 95, I have to do a 273 plus 95. Can never use Celsius. 368 degrees Kelvin. What is the new volume? So they're after this. Why do I have a column that's empty? Well, they didn't tell us that we added more particles or more or less. So the nice thing is I get to cross that off. Now I answer a few basic questions. What happened to the pressure when it goes from 981 to 54? That went down. What happened to the temperatures? It went from 308 to 368. That went up. What we have to do is we have to figure out what kind of effect would that have on our volume. And let's review this a little bit. The pressure, looking over here, the pressure is inversely proportional. It's the only one that's inversely proportional to the volume. So if you lower the pressure, if you take the pressure off something, it will get bigger. If you put pressure on something, it will get smaller. So the very fact that this pressure went down means that's going to cause the volume to go up. And I'm going to put a little P next to it. That means that the pressure caused that to happen. What about temperature? Temperature and pressure are directly proportional. If one goes up, the other will go up. So the temperature here is going up. That's also going to cause an increase in volume. So that one is going to be based on the temperature. What's next? Next thing is to do all the math. So I started with 5 liters. I'm going to put that over 1. How is the, I need to multiply it by the proportion created by both the pressure and the temperature. Let's take the pressure first. The pressure, I have to make sure that when I multiply something by pressure, that the pressure increases for this thing. The only way I can do that is to look at these two numbers and put the bigger number on top and the smaller number on the bottom. If the pressure is going to go up, I have to have the big number on top. How about the temperature? Same thing, the temperature needs to become bigger as a result of what I do, so I'm going to have 368 on top and 308 on the bottom. Now it's a long process, but the way I like to do this, press clear. Let's see if I can clear. Not sure where, there it is. The way I like to do this is just go all the way across the top. 5 times 981 times 368. And then any number on the bottom I divide. So divide by 54 and also divide by 308, and that equals 108.5. What is that? Well, it's a new volume. I didn't show all the cross-offs, but all of these ones, I didn't have to show everything, but it would have been kPa and kPa crossing out, degrees Kelvin and degrees Kelvin crossing out. The only thing left is liters, liters. Let's see if that even makes sense. I said that based on what's happening, that it's going to get bigger. It looks like that makes sense. That worked out. Slide this down. Try the next one. 3 liter at a temperature of 27, 273 plus 27 is 300 degree Kelvin, has a pressure of 680 millimeters of mercury. What will be the new pressure? So that's going to be in millimeters of mercury. If the temp is raised to 150 plus 273 is 423, and the volume expands to 5 liters. First, just what happened to the temp? It went up. What happened to the volume? It also went up. Then look for, okay, I can cross this off again, don't need the number of particles. Then how would that corresponding effect, what would that do to the pressure? Let's see how temperature and pressure are related. Temperature and pressure directly proportional. I'm looking down here, directly proportional. So if the temp goes up, the pressure goes up. How about the volume? The volume and the pressure are inversely proportional. It's the only one. Since the volume went up, the pressure is going to go down. I should have probably written a little t next to there. The temperature causes an increase, or I need the increase to be caused when I write that fraction. But the volume causes a decrease. Putting it all together, I'm starting with 680 millimeters of mercury, and I'm going to multiply by 1, 2 fractions. You know how I know? Because there's 1, 2 arrows underneath there. The temperature, okay, let's cut to the chase. The temperature has got to cause it to go bigger, so put the big number on top, 423 over the other temperature, which is 300. The volume, though, has to cause it to get smaller, so put the little number on top. Some people look at the arrow as an indication of, do I put the big number on top, or do I put the big number on the bottom? So next thing is doing the math. 680 times 423 times 3 divided by 300 and also divided by 5. 575.3 millimeters of mercury. How do I know it's millimeters of mercury? Well, it needed to be a new pressure. And since our original pressure was in millimeters of mercury, I'm going to keep that in millimeters of mercury. Sliding it down a little bit. Same story. 25 moles. Okay, we get to use the last column. 25 moles of particles. That's the number of particles of oxygen gas in a 15-liter container at 0 degrees Celsius. Don't write 0 there. You have to have it in Kelvin. That's 273 degrees Kelvin. Its pressure is 100 kPa or kilopascals. Half of the oxygen. Now, that would mean the number of particles. So half the oxygen is transferred to a different container. So when we're all done, we're only going to have 12.5 moles. Half of 25 is 12.5. Transfer to a 25, that's a bigger container. We're putting less particles in a bigger container. Heated to 300 Celsius. 300 plus 273 is 573. What will the pressure be in this container? First step, what happened to each of the things that I do have? The temp went up, the volume went up, but the number of particles went down. Next step, check your proportionalities to find out what effect will that have. If the temp goes up, the pressure goes up. And I'm going to write a little T because the temp caused that. What about the volume? Volume and pressure are the ones that are inversely proportional. So that means if the volume goes up like it did, the pressure will go down based on that volume change. Finally, the number of particles also is directly proportional. If we have less particles, we are going to have less pressure. Do I have particles? Everything is directly proportional except for the pressure and the volume. So the number of particles is going to have a inverse. So that's going to also go down based on the N. There it is, pressure and number of particles directly proportional. Okay, not there yet. Next thing is to do the math. If I started with 100, and that's kPa, kilopascals, I have to multiply that by 1, 2, 3 fractions. How do I know? Because there are 3 arrows inside of here. The first one about temperature, I need that to get bigger, so I'm putting the bigger number on top. The second one about volume is going to have to cause, the volume change is going to cause it to decrease, so I'm putting the bigger number on the bottom and the smaller number on the top. That'll make a fraction that makes it smaller. Finally, the number of particles is also going to cause a decrease, so I'm going to put the small number of particles on the top and the big number of particles on the bottom. Working through this math, I like to go right across the top. 100 times 573 times 15 times 12.5 divided by 273 divided by 25 and divided by 25 one more time, and I'm going to get about 63. I'm just going to write 63. 63 kPa. I don't really have a good reality check for this one because the temperature was going to cause it to get bigger, but the other two were going to cause it to get smaller. So I don't really know which one is going to win, so I'm just going to have to trust that. One more. Sample. Sample of gas occupies 2.4 liters. At 45 Celsius, 273 plus that is going to be 318, 310, 318. 300 kilopascals is my initial temp. Find the volume at standard temperature and pressure. Standard temperature and pressure, what are we talking about? Remember we took some notes about what standard is. Standard temperature pressure is a way for scientists to communicate with each other about the conditions that they may have done something in. Standard temperature and pressure, it just depends on which pressure scale you're using of what's standard. Since they chose kilopascals, I have to go find standard for kilopascals, which is 101.3. Even though standard temperature is 0 Celsius, we have to have it in Kelvin for it to make sense in these, for it to be truly proportional like we've written. So I'm going to write 273. That is standard pressure in kilopascals and standard temperature in Kelvin. Must have had the same number of particles. We get to ignore that. This went down. This went down. Pressure and volume are inversely, so the pressure going down will cause the volume to increase. That's based on a little p for pressure. But if the temp goes down, that would cause, they are directly proportional. Temperature and volume, I'm looking right over here, are directly proportional. Temp goes down, volume will go down based on the temperature. The math would look like this then. Take my initial volume, because I'm searching for the new volume. I need the pressure to increase, so put the big pressure number on top. I need the pressure to cause an increase in volume. And I need the temperature relationship to cause a decrease, so I need to put the Smaller number on top, 273 over 318. Clear. 2.4 times 300 times 273 divided by 101.3, also divided by 318, and I'm getting 6.1. 6.1 what? Well, we had liters, so then it's going to be liters. Once again, I don't really have a reality check to conflicting things. We're just going to have to go with it.